This video is going to cover a few basic principles regarding molecular orbitals. So if you recall in chapter 6, I discussed atomic orbitals. When I was talking about quantum numbers, I mentioned that orbitals exist in different subshells and thus have different shapes. So for instance, in the orbitals in an S subshell, or I should say orbital, is just spherical. Remember, there's only one orbital in an S subshell, but in a P subshell, for instance, orbitals are shaped in what's called a dumbbell shape. And if you recall, there are 3 orbitals in every P subshell, and they overlap each other in a manner like this. Now, those are for individual atomic orbitals. But what happens when atoms bond and form molecules? Well, there's going to be some overlap of these different orbitals. And the way that they overlap determines what type of molecular orbital forms. Now, orbitals in D and F subshells certainly do have different shapes, but you won't have to worry about that for this class, so I'm not going to get into that right now. For this lecture, I'm just going to be focusing on S and P orbitals, because that's all you're going to have to worry about. So, if 2 S orbitals overlap, that forms what's called a sigma bond. So this is the Greek letter sigma. It's a sigma bond. If you have an S orbital overlapping with a P orbital, that also forms a sigma bond. If you have 2 P orbitals overlapping head-on like this, that also forms a sigma bond. So as you see, there are many different ways that sigma bonds can be formed. However, if you have 2 P... Oh, I'm sorry, I should have drawn these in green, but you get the point. If you have 2 P orbitals that overlap parallel to one another, where the long axes are no longer kind of run into each other, they're instead running parallel, that is now a pi bond. So the 2 types of molecular orbitals that you will have to worry about are either just sigma or pi. So let's take a look at a molecule to kind of look at those in action. So I'm just going to show kind of a basic molecule here to start. So 2 carbons double bonded to each other with hydrogens off of it. Off of each of them, I should say. Okay. Now, remember, the only electrons that are actually involved in bonding are valence electrons. So to know what kind of orbital each individual atom is going to be using, we need to know what orbitals with valence electrons exist in. So hydrogen, remember, is in the S block, so its valence electrons are in an S orbital. Carbon is in the P block, so its valence electrons are in P orbitals. So each hydrogen is going to have an S orbital here that's involved in the bonding. And I'm not going to draw all the P orbitals for the carbons because they get pretty cluttered and be hard to see. But remember, they do have these 3 P orbitals each, and effectively you have a lobe from each carbon that interacts with the hydrogens. So each of these 4 bonds fit into this category. It's an S orbital overlapping with a P orbital. So each of those are sigma bonds. Now between the 2 carbons, they each have a lobe that are going to be head-on interacting with one another. And if you recall, that is also a sigma bond. But they will also have lobes that will kind of run parallel with one another, and that is going to form pi bonds right there. And that's actually where the electrons in the second bond for the double bond come into play. So now, if one thing you might be asked to do, or you will be asked to do, is identify how many sigma and pi bonds exist in a molecule. And that may sound a little complicated, but it's actually pretty simple. So let's I'll draw a random molecule to start with. Okay. So where you want to start is every bonding site. If you recall, when I was talking about geometry, I said any, so there I was talking about any potential bonding site. But here I'm talking about any bonding site. So a double bond and a triple bond still only count as one bonding site because they're still bonding the same two atoms. There's just extra electrons there. Count every bonding site once for sigma bonds. So, one sigma bond, and I'm just going over one of those two double bonds there because I'm only counting that site once right now. 3, 4, 5, 6, 7. That is 7 sigma bonds. So basically 7 bonding sites, 7 sigma bonds. Then, however many bonds are left over are going to be pi bonds. So basically, you'll only have pi bonds if you have double and or triple bonds. And basically all of the extra bonds beyond just single bonds are what make the pi bonds. So we've already counted 7 of these bonds. Here's one more. Here's a second one that we haven't counted yet, and that's it. So there are 2 pi bonds. And that's all you have to do to figure out how many sigma and pi bonds exist in a molecule.